I'm bkoep here at the Institute for Protein Design with E&H. We're here for our second installment of Foldit Lab Reports. We had some great feedback from Foldit players on the first one. Thank you very much for your kind words. I'm excited to get to some of those comments at the end of this video. Again, we are looking for constructive criticism, so if there are things that you want to see, tell us, and we'll do our best. News this week. We are introducing a new member of the Foldit team. We have Ari Cohn, 821, coming to us from the University of Denver.
Hi, my name is Ari. I will be working as a community liaison. I am here to address any concerns that you have within the Foldit community, and I can also act as a point person working between you all and the individuals who work behind the scenes at Foldit. So if you have any questions or concerns or anything that you would like to discuss further, please feel free to reach out to me.
We are super excited to have Ari on the team. We also have some annoying news. If you've updated your Mac operating system to the latest operating system,
it's Mac OS Catalina.
You can no longer run the old 32-bit version of Foldit.
I think we've nailed it.
We've updated the installer on the front webpage. Please, if you do upgrade your operating system, download the new installer and see the instructions below for transferring over your recipes and some of the puzzle data from your old version of Foldit. Also, I have a question for you about how you feel about how we talk about player usernames when we talk about data analysis in Foldit. So please see the poll below and let us know what you think. What this comes down to is a lot of times we want to share our take on some work of Foldit players, and usually Foldit players, you'd like to know, who made this model, who's responsible for it. And we just want to know how you feel about sharing usernames when we talk about Foldit data analysis. Next, we have some puzzle updates. So this month we have 3 puzzle updates on the IL-7R binder designs, the Aflatoxin puzzle, and the Symmetric design. We finished up bkoev's series with the IL-7R binders. So bkoev is going to take all of Foldit players' work, and he's going to put together an order and order thousands of proteins and test them for binding to IL-7R, and we'll have some data for Foldit players when that experiment gets underway. We saw the return of Aflatoxin puzzles. The Siegel Lab has a new strategy for degrading aflatoxin. So Foldit players, they spent 2 weeks designing a new loop to bind aflatoxin on a brand new scaffold. We have done some preliminary analysis on those solutions and shipped them off to the Siegel Lab. The Siegel Lab has taken a closer look, and hopefully will get back to us on some feedback so that we can do more rounds and explore some more options for degrading aflatoxin. Lastly, we had a lot of symmetric design puzzles. I hope you guys aren't sick of them yet, because I think we'll have a lot more. This is more of the same. We're looking at reducing the size of the interface between Foldit chains. And that actually brings me to our lab updates. It's just the one. We have a lab update. We have ordered some new symmetric designs from Foldit players for testing in the wet lab. These are mostly dimers, symmetric dimers with 2 chains. And these have things with alpha helices and beta sheets. And we also ordered a handful of trimers, which have 3 chains that come together. And these are alpha helices and some other topologies. So we're really looking forward to seeing how these behave in the lab. These have some different properties than some previous designs that we've tested. In particular, they have smaller interfaces that are a bit more polar, so we expect these proteins to be a little bit more behaved in the wet lab, although there's a chance that they won't associate as tightly in their oligomeric state. I wanted to review some principles of symmetric design, so I thought we could look through a few designs from a recent puzzle in September. This is puzzle 1733, symmetric trimer design, 70 residues. And I have on my screen a few designs from Foldit players. First up is this very creative looking design, a nice mixed alpha-beta topology. And we see that this design has a nice limited interface. We don't have a huge interface between symmetric chains, just a nice healthy one helix kind of that interfaces with the rest. A concern with this design is that this helix at the interface, here if I turn off symmetric chains, this helix at the interface and the monomer is almost completely hydrophobic. We'll notice that all of the residues on this helix are orange. This is a little bit of a concern for us because those residues will not want to interact with water. So when this monomer is translated by the RNA and it's trying to fold on its own, we're a little bit worried that this helix might not fold as this player designed, or that if it does fold, all of these orange hydrophobic side chains will end up sticking to other things in the cell rather than forming this well-behaved trimer like the Foldit player designed. And so this is in part what we've been trying to get at with the recent limited interfaces. We'd like to see more polar residues instead of these large patches of hydrophobic residues on a protein, which makes them poorly behaved in the lab. Next up, I want to talk about buried edge strands. So here on my screen, I have another trimer design from the same puzzle. This one also very cool. We have a completely beta sheet protein that is designed to come together in this trimer. What concerns me mostly about this design is that this edge strand here at the interface is buried. This is underappreciated. If you're viewing your protein in cartoon mode, then you probably don't see these atoms a lot. But we have to remember that sheet atoms, or that beta sheets, have polar atoms along the backbone. So here we see that there are oxygen and nitrogen atoms all along this beta sheet that are packed against a completely hydrophobic surface on the neighboring monomer. So this is a problem. These polar residues will want to make hydrogen bonds. They'll either want to make hydrogen bonds to water or to other polar atoms in the protein, either within one monomer unit or the next symmetric monomer unit. But this is a problem when we have any polar atoms on a side chain, on a backbone. If it can't make hydrogen bonds with the surrounding water or with other polar atoms, it's going to be very unstable. Lastly, I want to talk about a design that I think meets all of our criteria for a symmetric design. So here we have a design very much like the first one in topology. We have a beta sheet with two helices, and the interface between units is mostly mediated by this one central helix, which is of course copied in the symmetric units. The difference between this one and the first one, let's see, if we look at just the monomer unit, is that this helix has some polar residues sprinkled throughout. So instead of this helix being completely nonpolar, completely made up of orange residues, we see that it has some blue residues sprinkled in it. This is nice because it means that this monomer will probably be more behaved in solution. There's still a significant patch of these orange residues, which are still available for binding. So we think that there's still a good chance for these proteins to bind each other in the trimer. As Foldit players know, this does become tricky because, like we just said, all of these polar atoms have to make hydrogen bonds. And we see actually a kind of nice interaction here at the interface with a semi-buried tyrosine and an arginine, which is bridged by a polar residue in the neighboring unit. So we like this design because it has all of the polar atoms seem to be satisfied. They're making hydrogen bonds either with other polar atoms in the protein, or they can make hydrogen bonds with the surrounding water. We like that there are no vast swaths of nonpolar orange residues, but there is still some hydrophobic patch that allows these three units to come together and bind each other very tightly. So our hope is that this all strikes a balance, and that if we express and purify this protein in the lab, then it will behave exactly as the Foldit players have designed and come together in a well-behaved trimer. So in the coming month, we'll be running more of these symmetric design puzzles. I'd like Foldit players to try to focus on these principles, and especially looking for these buried polar atoms that can't make hydrogen bonds. These are very problematic in Foldit. We probably will have some tools in the pipeline coming soon to help address this, but for the time being, we want to see what Foldit players can come up with. So give us your best designs. Remember to share them with scientists. We always look at the shared with scientists solutions. We love to see what Foldit players are excited about, not just what scores well in Foldit puzzles. So real quick, I wanted to address some of the comments we got last month from Foldit players. We had some great questions from Ninja Greg and others. One thing that is clear is that Foldit players are very interested to see what they've personally contributed to, or what their group has contributed to. So please look at the poll below, which should help us think about how we share Foldit usernames and responsibility for some of the work that goes on in Foldit. Yes, please leave comments below on the Foldit website, on the YouTube website, about what you'd like to see in future videos.